Right, it's example 5 and 8.1. I didn't assign any of these log questions, at least in the kind of modified assignment there, but they are really important because they give us an actual real world use of logarithms beyond the pH or POH scale, which we're going to leave to chemistry. Anytime we use a logarithmic scale, or not anytime, but typically when we use a logarithmic scale, it's because there's a very, very large range of values that are tough to graph with any type of meaning. So in this particular case, we are talking about the magnitude of an earthquake being equal to log base 10 of the amplitude of the ground motion compared to kind of what we call a base amplitude. A naught is essentially, it says A naught is the amplitude corrected for the distance to the actual earthquake. I really like the idea of thinking of A naught as like a baseline earthquake, that's kind of the smallest earthquake possible. And we'll see that in a decibel question a little bit later as well. The first thing I want to do though is I want to use a little bit of subscripts that if we talk about the magnitude of earthquake X, that's equal to log base 10 of the amplitude of earthquake X over A naught. I'm going to put a bracket around that. Now that is typically given to you in a question, but what's just as useful is switching that into exponential form. And we get that 10 to the power of the magnitude of the earthquake is equal to AX over A naught. We're going to use this a little bit later in the question, and it does actually make a part of the question much, much easier to work with. But before we do that, let's get through kind of A and B. It wants us in 1946, an earthquake that struck Vancouver Island. It had an amplitude that was 10.73 times A naught. And I want to identify that what that's saying is that 10.73 is equal to the amplitude of the Vancouver earthquake over A naught. So if we want to find the magnitude of the Vancouver earthquake, that's going to be log base 10 of AV over A naught. In this case, the 10.73 can be substituted in. So the magnitude of Vancouver's earthquake in 1946 was equal to log base 10 of 10 to the power of 7.3. Now, keep in mind what that logarithm is asking. That logarithm is asking, what exponent do I put on the base, which is 10, even though we don't write it, to get the argument 10 to the power of 7.3? Now, I always like, switching this into exponential form just so students see how maybe straightforward it is, that this equation is saying that 10 to the power of the magnitude of the earthquake is equal to 10 to the power of 7.3. So the magnitude of our earthquake is 7.3 on the Richter scale. Right? A is definitely designed to be pretty direct, and we can kind of just, plug things in. All right, the next question, B here, says the strongest earthquake in Canada struck Hattagawai off the coast of BC in 1949. It had a Richter reading of 8.1. So for B, we know that the magnitude of the HG earthquake was equal to 8.1. They want to know how many times great is A naught. So what is the amplitude of HG divided by A naught? And it's why I wanted to put this formula up here. We are going to use, and I'll drag it down, this guy is essentially the formula that we're going to use for this question, because in this particular question, I know I have AX over here, but keep in mind that X is any earthquake. So maybe I'll make this specific to this question, that 10 to the power of the magnitude of the Hattagawai earthquake is equal to the amplitude of HG over the amplitude A naught. Well, we know what MHG is. It's 8.1. So we're going to substitute that in, and I get that 10 to the power of 8.1 is equal to the amplitude of HG over the amplitude of amplitude of A naught. Now, depending on what the question asks, some questions will put an actual value in there. If you do that, you just have to put in 8 to the power or 10 to the power of 8.1, and I get it's a pretty ridiculously large number, 125,892,541.2. That's how many times greater than A naught the amplitude of that Hattagawai earthquake is. All right, now we're going to use those numbers, and we're going to kind of keep them in mind. I'm going to put them down here for C. I want to write those two values, that the amplitude of Vancouver's earthquake over A naught was 10 to the power of 7.3. The amplitude of Hattagawai's over A naught was equal to 10 to the power of 8.1. Because what C wants us to determine is compare the Hattagawai earthquake with the earthquake that struck Vancouver Island. So we are going to find out how many times worse the Hattagawai earthquake was, or how many times bigger AHG is compared to AV. Now, I want to put that if we take the amplitude of Vancouver's earthquake and we multiply it by some unknown X, I get the amplitude of the earthquake in HG. Well, a much better way to deal with that algebraically is to put that ratio side by side, or I guess, underneath each other in a single fraction. Now, what this means is, we know AHD over A naught and we know AV over A naught, but essentially we want to compare those two earthquakes to each other. So we want a statement along the lines of saying that Haida Gwaiy's earthquake was 43 times worse than Vancouver's earthquake. People love comparing things like that, and logarithmic scales help us do that quite a bit. Now, the way that I'm going to do this is I'm going to manipulate what I just circled in red to actually contain these two expressions. And the way that I'm going to do that is something that you've done again and again and again in math classes, which is to take that fraction and multiply the top by 1 over A naught and multiply the bottom by 1 over A naught. Now, the reason I can get away with doing this is what I am putting into a blue box there is equivalent to 1. So I'm not changing the value, I'm changing the appearance of my expression. And I get, when I do that, that the amount of times greater Hg is than V is equal to the amplitude of Hg divided by A naught divided by the amplitude of Vancouver divided by A naught. And the reason why that's so beneficial is we have expressions for those. So the number of times greater that Haida Gwaii is compared to Vancouver is going to be the result of 10 to the power of 8.1 divided by 10 to the power of 7.3, which is 10 to the power of 8.1 minus 7.3, or 10 to the power of 0.8. Now, that's not typically how we want to present information, 10 to the power of 0.8. It's like you're giving people homework when you talk to them. What I would say instead is the amplitude of Vancouver's earthquake multiplied by that x. I'm going to put that into my calculator. 10 to the power of 0.8, I get 6.3095. So the amplitude of Vancouver's earthquake multiplied by 6.3 would give me the amplitude of Haida Gwaiy's earthquake. Now, if you talk about this in language, I'm saying that the amplitude of the motion in Haida Gwaiy's earthquake was 6.3 times the amplitude of the seismic motion for Vancouver's earthquake. And being able to relate those to each other is really useful. It can help us to predict the amount of damages, the amount of loss of life, whatever's happening in that earthquake, and hopefully we can get humanitarian aid out quicker, and a lot of other things. Just as a weird kind of factoid, there was an earthquake in, I think it was San Francisco, and eventually the tremors reached another city, but people felt it in San Francisco and they tweeted about it, and that actually gave people early warning in the other city because that tweet traveled at basically the speed of light, or the speed of type plus light, I suppose. Okay, I'm going to put the standard assignment up there. Make sure you are checking Google Classroom in case it's modified. Good luck, and please do ask any questions that you might have.